speaker is Egbert Rijke from Carnegie Mellon University. Actually, I don't know. You are the philosophy department.
Yes, I'm a student of Steve.
Yeah, a student of Steve Howley. Egbert will speak about an algebraic formulation of extension types.
Okay. Well, thank you very much, Vladimir, for having me. I'm going to speak about research that I mostly did last year, following on a theorem that I proved in Homotopy type theory, which is called the descent theorem. And there I was investigating the graph model of type theory, which is an internal model of type theory, and I analyzed this structure of this type theory of this model, and I found certain algebraic operations, which I'm going to tell you about, and consequently that I try to reformulate type theory in an algebraic way. Using the usual style of name-free type theory. And the corresponding algebraic objects are called E-systems, because last year I was talking about this in Paris with Vladimir, and he was at the same time working on a thing which he calls C-systems and B-systems. And E-systems are something similar. C-systems are categories of attributes which were introduced by Cardinal in the 70s or 80s. So I'm going to do two things in this talk. I'm going to present you this version of type theory, which has no type constructors at all. It just has a structure of type dependency. And I'm going to tell you what the corresponding algebraic object is. Okay? I already mentioned some discussions with Vladimir that I had in Paris, so I'm very grateful to him. Also to Richard Garner, whom I discussed this topic with Steve Howley, who is my supervisor.
Does the E in E-system stand for Egbert?
No, this name, the E stands is the letter following the D, and there is also a D system which is
from UDF.
From UDF.
Category with family.
There's no F system.
There are no A systems yet.
No, it's just pragmatic. I didn't defend this name, I guess. Okay. So there we go. So we're going to reformulate type theory. So what do we want from it? The first thing that I wanted to go for is that the meta theory should be as weak as possible. And I should not require, in particular, natural numbers to formulate it. So I should just know how to handle inference rules, but nothing else. That should be it. That should be strong enough to give you type dependency. Whereas in usual formulations, you see at some point natural numbers popping in to talk about dependent context, for example, or to talk about context of arbitrary length. That's not in this system. There has to be, consequently, there has to be finitely many sorts. In this case, there will be only contexts, families, and terms. So there are going to be just 3 sorts. Which means that in my categorical implementation, in the category finite limits, I will have 3 objects for categories, for families, and for terms. It has to be algebraic. Because then you can use tools from algebra. So that's a great merit that I wanted to keep. So the operations are going to be algebraic operations, and they are either homomorphisms or they fit nicely. They can be seen in some way as homomorphisms. All of them can be homomorphisms. Okay, a finite set of rules, in particular no funny rule schemes. So all the rules that I'm writing, those are the only rules that will be there. Okay, so from the fact that it's algebraic theory, you can immediately apply standard tools of algebras, such as you get free algebras of this kind, you get quotient algebras. and all sorts of stuff like that. It also exists for C systems, about which Vladimir recently wrote some papers that are on the archive now. My work is not yet on the archive, so this is the first opportunity to see it. The major source of examples, as I mentioned, are B systems or C systems. Vladimir recently published a paper in which proved that every C system can be seen as a B system, as a pre-B system, and the functor which assigns pre-B system to a C system has precisely the B systems as its image. So this is work of Vladimir. And when you look in that paper, the axioms that I'm going to present here are exactly the same as the axioms that he wrote down in his article on B systems. So
B systems get infinite domain, of course.
yes.
Which is
Yeah. So there are some things different, and I will come back to that. One big wish of me when I was developing this, because I was working on internal models at that time, I wanted that there was also a notion of internal E-system available right off the bat without needing to introduce any type constructors. It should be possible to say what an internal E-system is. And that worked. I'm not going to present that here because it will take way too long. I'll just tell you how to implement this theory in a category of finite limits. But there is also an internal version of this. So there are internal models of this theory. If anything you should remember from this talk is this picture. It's how the theories fit into each other. At the top we have the theory of extension, where you have context extension and family extension. There are basic operations. They give rise to type dependency with higher and higher families. Based on the theory of extension, you can formulate three new theories: the theory of weakening, the theory of substitution, and the empty context and the empty families. The last one I'm not going to talk about here because, well, I need to make some choices for a talk. So I will only tell you what the theory of weakening is and what the theory of substitution is. But I do have the slides of empty context and families prepared. So if you have any questions about it at the end of the talk, I can show you them, and then you can ask questions about it. Okay. Under the theory of weakening, you see the theory of projections. There you introduce identity morphisms, well, together with weakening, they give rise to arbitrary projections. And then at the bottom, when you join all these theories and you make everything compatible with each other, you get dependent type theory. So this is the structure of the theories, and at the end of this talk we have an explanation of what dependent type theory is. So if you are already familiar with type theory, you are going to see a reformulation of type theory. If you are not already familiar with dependent type theory, you can, well, I hope that you learn something about dependent type theory from this talk, how the structure goes. Oh yes, so this says that these three theories of weakening, substitution, and empty are independent, but I sort of said that. Okay, so to get things started, we need judgments, because that's how type theory usually goes. You have the judgment that something is a context, and we usually name that gamma, and the judgment that two contexts are equal. I always use a triple equality sign. Then something can be a family in a given context, and something can be a term in a family. And a family should be thought of as a vibration, and the term can then be thought of as a section of the vibration. Alright, and you have the corresponding judgmental equalities for those. And these judgmental equalities, they are all equivalence relations and convertible. And an example of a convertibility rule is that if gamma and delta are equal contexts, And in gamma you have a family, then the same family is also a family over delta. So likewise, if A and B are equal families, and X is a term of A, then X is also a term of B. These kind of rules are sort of standard and are always assumed, so here I'm going to be a little bit quick. Okay, so how do you implement this in a category with finite limits? You take three objects, one object C for the sort of context, a second object F for the sort of families, but every family has to have a context, so you have a map F, which Van Meer always calls FT, so I will use this name too. You have a morphism FT from F to C. And likewise, T, you have the object of terms, and delta says of which family this term is a term, right? Because terms are always have a type. Okay, so let's compare this with B systems. In B system we have such an infinite tower which goes on forever, which has, well, here's sort of the context, and then terms of this thing, and then families over that context, and then terms of that. And then higher families and higher terms. And you have such an infinite structure, and the merit of that is that you don't need extension. You can go without extension. But you do need then natural numbers. So that's the payoff, and you get such a nice stratification. In the situation of E-systems, it sort of looks simpler, but we do need extension operations. So I'm going to tell you now what extension is. Is everything clear so far? So context extension assigns to a family in a context A a new context, which you call gamma.A. And there's an equality rule that says if gamma and delta are equal and A and B are equal, then those extensions are equal. This sort of administrative rule that doesn't have too much content, but you do have to require it because it doesn't follow. But there is also a family extension, which says that if you have a family P over an extended context gamma.A, then you can make a new family A.P, and this is a family over gamma. And this family extension I want because I want the whole theory to be stable under slicing in some sort. Like you have a familiar theorem in topos theory that this is again a topos, where every object X of E. I want the very same structure of type theory in any context, so I need to add family extension. And this will be very useful later on. So now you can require that extension is associative. So you can either first extend A with gamma to have a new context, and then the P, or you can family extend the A and the P first, and then context extension with gamma. And the second rule you also need it, well, to ensure that you have stability of initializing. Okay, so these are the only rules for extension. You only say that it's associative. So in a category with finite limits, you are going to have two more operations, E0 for context extension and E1 for family extension. So that's here we use that we have a category with finite limits because the E1 has to be a family over an extended context and then assigns a new family. So what does that mean in their category? This family here, F, E0, F, this consists of pairs A and P. such that E naught of A is the underlying context of E. So that's saying exactly the upper thing of this rule. So that's why you need, in particular, this this pullback. Okay, and then the output is a new family. But we need to know something about this family because the underlying context of this new family is gamma itself, and so there's going to be an equation, which means a commutative diagram. And the commutative diagram is this one. The underlying context of a family extended thing is the underlying context of the underlying context. So in this pi 1, you take the A, and then this foot, it tells you go to the underlying context of A, which is the gamma. And then the upper thing says, well, first you extend, look at the underlying context, it has to be gamma again. So this diagram has to commute. Okay, but this doesn't say anything yet about the associativity. That's why I call it a pre-extension algebra and not an extension algebra. Okay? So here we see that we can have a notion of higher families, like the P, which is a family over an extended context. And we are going to call this thing F2, because it's sort of families at the second level, second family. And the pi 1 over there is going to be called, it behaves very much like a ft, so we are going to call it ft2. And that's what I'm going to do here. Furthermore, we have families at the third level and at the fourth level, and you can define them using pullbacks. So a term of F3 is a pullback of pullbacks, so it consists not of pairs, but of, well, it consists of pairs of pairs. So what is a thing in F3? Let's write down a typical element of that to get a sense of what's going on. It is a pair of pairs because it's pullbacks. And then in the F2 you have the AP. But now, here we have a family such that we extend this. It is going to be the FT2, which is the first projection of the second one. So we extend this one. And that's the first component of this, and then we are free to have the other. So the F3 consists of such objects.
So gamma ATQ.
Well, so there's a gamma even earlier. But yeah. Yeah, so in type theory you would write gamma A, B, Q, phi. So this would be the type theoretic notation, yeah. Okay. And then FT3 looks at the first component of that, so it takes out the AP. Okay. And now we can have an even higher extension. That's so we have the family extension, but we now have also extension for F2, which we can define, which is going to be important. So I'm going to explain you how this diagram works. At the F3 level, or at the F3, we had the A, P, Q. Then this is mapped by the upper map by looking at the second component 2 times. So this is going to be mapped to PQ. And then you extend this with the usual family extension. And the foot of this is going to be gamma.A. Alright, and then if you go in the other direction, you look at the other thing, AP. Now the FT is looking at the first component again, so you are going to be map this to A, and then you extend it, you get to gamma A dot B. So, but this thing here is a pullback. So we get from this, we see that this diagram commutes. So we get to a new thing in F2, which is called A P dot Q. That's what we get, right? So this is how this diagram works, and the E2 is exactly extending the P and the Q. So it picks out the right things and extends. Okay? So that's, and you can do this at every level you want. So there are going to be a lot of this sort of diagrams in this talk, so because you need to express things in categories with finite limits. Oops. So E2 is going to be that unique morphism. Then an extension algebra to express the associativity. Well, there are going to be there were two rules for the associativity. One at the context level, one at the family level, and then one of the rules you saw this P dot Q appearing. Yeah, so one of the rules was A dot P dot Q is the same thing as A dot P dot Q. So here we needed to have access to the E2. So that diagram on the right there is the second rule for the associativity. And the diagram on the left is the first rule for the associativity. Okay, so an extension algebra is a pre-extension algebra for which furthermore these two diagrams meet. Okay, and before we can continue, we need to develop a little bit of theory of extension algebra, because weakening and substitution are going to be homomorphisms of extension algebras. So we need to know what these homomorphisms are. We need to know, we need to not have that structure that is close to their slicing. So that's a second property that we want. And we also want to know that it's stable under change of base, because that allows for parametrized homomorphisms. And both weakening and substitution are examples of those, as we will see later in the talk. So I'm going to develop these three things, and then obviously. So pre-extension homomorphism is the morphism for pre-extension algebras is going to be a triple which maps the fundamental structure of the first to the fundamental structure of the second, and these diagrams have to commute. But not only that, the F also has to be compatible with the extension. All right. So this means that if you apply F to an extended thing, then you get an extended thing. That's what these diagrams are saying. That it's compatible with extension. And these will be rules that are true for weakening and substitution. So that's why you have them. And then you can see from this structure. Oh, sorry. There's another slide. A pre-extension homomorphism between extension algebras is just an extension homomorphism. So you just look whether the codomain and the domain are both extension algebra and call it an extension homomorphism. Okay, so I was telling about this slicing structure. So given this fundamental structure, together with the extension operation, can we sort of go up? And yes, we can. We can go up to the level of F. Take the F2 as the higher families, and the T2, which are terms over the higher families. So that's just another pullback. So this pullback just means that it's a term, and the type of which it is a term. If you look at the underlying context, then that's an extended context. That's all there is. likewise the delta 2 is defined by pullback. And the extension operations in this case are going to be E1 and the E2 that we saw earlier, that we defined using pullback. So this you can continue forever, and that sort of gives you the infinite tower of these systems, almost, well, practically yes. So you have a theorem if CFT is an extension algebra, so these associativity condition hold, then they also hold for the structure that we just defined, the f of CFT. So that's good to know. And there's another lemma, so we don't really need it, but it says that a pre-extension algebra is an extension algebra precisely when these two things here are pre-extension homomorphisms. So that just means that E not preserves the extension structure. Okay, so this is how you can see extension as a homomorphism. So the extension corresponds in category theory, in plane of category theory, to sigma, and the sigma also is a functor which acts as identity on homomorphisms. And that's what you see here too. It's just a projection. There's nothing on the higher levels. So it's analogous to that. Okay. I'm going to draw commutative diagrams in the future, and they can have both objects and extension algebras in them. So if I draw such a diagram on the top, and I say that it commutes, what I really mean is that we have the P going from the sort of context of CFT to some X, and likewise you have T prime, and only the bottom diagram commutes, but in fact you have some more layers. But that's useful because now we can express universal properties quite efficiently. If you assume that you have the pre-extension algebra CFT, and you have this morphism down to X, and the object Y with the morphism into X, then you can pull back the whole structure. And the universal property is that whenever you have a morphism F from the CFT prime to CFT, and the morphism down to Y, such that the diagram commutes, and there's a unique pre-extension homomorphism mapping into the change of base of that thing. Okay, so that's the change of base. And there's theorem if you apply this change of base operation to an extension algebra, so you have the associativity conditions, then you get again an extension algebra. One more theorem. If you so you can apply this F operation that looks at higher structure. You can apply it as many times as you want. If you apply it 2 times, you get something that's equivalent to a change of base. And if you apply F to something that's already a change of base, you get the change of base. So these things commute. Okay, so this is all we need to know about extension algebra. We can now go to the theory of weakening. So we will introduce a theory of operation of weakening, and because it's going to be a homomorphism, it will act on all the 3 levels of the context of the families and of the terms, just like homomorphism does. And when B is weakened by A, I'm going to denote this by A in funny brackets B. Weakening will preserve extension, and this is just saying that weakening is going to be an extension homomorphism between extension algebras. And there will be a notion of currying for weakening, which explains when you weaken something by an extended object, the A up there could be a dot p really, right? You can weaken by a dot p. And then this rule says what happens in that case. And with these three things, you have a notion of pre-weakening algebra. Well, they satisfy the implementation of these things. There is a notion of pre-weakening homomorphism. And then we'll have again theorems that say it's stable under change of base and stable with this f under slicing. So it will make then sense to require that weakening itself is a pre-weakening homomorphism. And if that is the case, you call the pre-weakening algebra a weakening algebra. So the only thing that differs in that is the difference between a pre-weakening algebra and the weakening algebra is the requirement that weakening is itself a pre-weakening homomorphism. Why do I have to make so many steps? Well, for the first there are just so many rules, and then I need to then weakening needs to be compatible with itself, and the only way to introduce this conceptually, to make this conceptually clear, is by saying that it's a homomorphism of algebras of some kind, and the kind is pre-weakening. Okay, so it's going to be that. Okay, so weakening is by a family, as we sort of introduced. When you have a family A and a family B, both in the same context gamma, then you can weaken A by B, and you get a new family, which is over gamma dot A. And there's an equality rule for that. And we said that we are going to have this is going to happen at 3 levels, so I will need 2 more rules. What if I have a family Q over the B? Then I can weaken that 2 by A. And if I have a term of that, I can weaken that term too. So these 2 rules are here. If I have the Q, then the A weakened by Q is going to be a new family over gamma A, but now it's going to be a family over gamma A dot B, but weakened by A. And likewise, if you have a term G of Q, then you get a term A weakened G of this weakened family. Okay? So there's these 3 things. And then weakening preserves extension, which I sort of, this is the rule. If you have some function and preserves extension, then it distributes over extension. So that's what's happening in these rules, exactly the same. If you have Q over B, and you weaken the extended thing, then, well, the weakening distributes over that. And that only makes sense if you have weakening, a family action of weakening. And the second rule says sort of the same, but for family extension. Okay, so these things just say there's a weakening operation. So what's the domain of this weakening operation? The domain is going to be, it's going to have a family over some context gamma, and over the same context gamma, you have another family. But here on the second side, or on the right side of the fullback thing, you must have the whole structure of that theory. So the thing on the left is just the sort of family, families, and the thing on the right is the whole CFT algebra, the whole extension algebra. So this is why you need to change the base, and this is going to give you a value at level 2. So this is how you do that in the category finite limits. And then you know something about the underlying context of the new family that you get, and this is expressed by the bottom diagram. If you weaken and you look at the underlying context, you see that it's going to be A. So this means if you start with A and a B, and you weaken that, you get an A, B, then the underlying, then this FT2 is going to give you the A, and that's just the project. So that diagram has to commute. that you can just read it off from the rules. Okay. So I was talking about the scurrying rule, and the weakening is in itself done via an extended family. When you do this, you just apply weakening twice. So weakening by A dot P is first weaken by P, first weaken the thing by A, then weaken that by P. That's just how it goes. This is an equation of homomorphism, so there need to be two more versions of this rule. What if you have a Q over B and the term of that? But that's, the essence is the upper thing. This is going to be a diagram. Now we see that we are not, in the upper rule, we are not weakening only by A, but also by P. So we need to find a new operation, which is weakening on the family model. So I said that at the bottom. We need so the weakening on the CFT we have, but we also need the weakening on the F, on the slicing of that, to express this rule, just to express it. So that's what I'm going to construct next. In this this diagram, it's way too complicated to understand it now because I'm going to skip over it. That's the only thing that it does. I marked it in red. That's the only essential thing. It picks out the right stuff, then it weakens, and you use the universal property to go back. So it's not too important. I'm only showing you how you would define it. It's just by pullback. Oops. So to implement this currying rule, you are going to draw a new commutative diagram. The diagonal thing, which is curved, is saying you weaken by something which is extended, and the upper thing is saying weakening twice, and that has to commute. And all the fluff around it, just make sure that you have the right domain and codomain, but it's doing nothing. We just defined the pre-weakening algebra. Pre-weakening homomorphism is extension homomorphism which is compatible with this weakening operation, and that's exactly what we want also for the weakening itself in the end. So to express that weakening is compatible with itself. So what do we need? We need the theorem that says the f of a pre-weakening algebra is again a pre-weakening algebra. The change of base of a pre-weakening algebra is again a pre-weakening algebra. And then it makes sense to require that weakening itself is a pre-weakening homomorphism. But you need to do this work. There's no way around it. With the slicing we already had it. With the change of base you can define it with a similar complicated commutative diagram that I'm going to skip, so I don't have much time. And the theorem says that if you do this on a pre-weakening algebra, the results you get a pre-weakening algebra. So these equations that you required hold again. That's the content of this theorem. Okay, so if CFT is a pre-weakening algebra, so is FT. We already sort of saw that. And therefore it makes sense to require that the weakening operation itself is a pre-weakening homomorphism. So we do that and we arrive at the notion of a weakening algebra. And then you have again these two theorems. This condition is stable under change of base, and it's stable under slicing. Okay, we've had this condition that weakening is compatible with itself. How does it look in type theory? It looks like this. If you weaken twice, then you sort of weaken twice again. That just means that this A here is distributing over the weakening. That's what's going on, right? The A distributes over them. And that's exactly the requirement that weakening is weakening homomorphism. So there are two more versions of this rule because there's 3 of everything. Okay, then the theory of projections, where we introduce identity morphisms. They are sort of fiberized identity morphism, but really just identity morphism. We call them units. When you weaken a unit, you get an arbitrary projection, so that's why I call this the theory of projections. There will be again first a version of pre-projection algebras, where you have an implementation of this unit. Then I will define pre-projection homomorphism, where the unit is preserved, and I will second then require that weakening is such a pre-projection homomorphism, and if that's the case, we call it pre-projection algebra, projection algebra. Okay, so there's always this structure to get the thing going. So how are they introduced in fact theory? If you have a family A over gamma, then you get it A, and it's a term of A weakened by itself. So it's like a morphism from A to A, and this is how you express it in the rules. Okay. And the fact that weakening preserves the structure of identities of units says that we can weaken by A an identity, and you get identity on a weakened thing. Well, that's a fact of life, but you have that. So I'm going to rush a little bit through this because we don't have much time. A pre-projection algebra is one where you have a term or a morphism I for the unit that goes from a family to a term at level 2. And there's to compute some diagram. First you go down with the diagonal to go to the family A, comma A. The fullback is with 2 times foot, so it's not the F2. Then you weaken this thing, and that's the type of unit. Okay, so that's just a commutative diagram. Then a pre-projection homomorphism is one that preserves the I, so this diagram has to commute. And then a projection algebra is one for which weakening is itself a pre-projection homomorphism. And a projection homomorphism is a pre-projection homomorphism between projection algebras. So this whole thing gets repetitive, and that's a good feature, right? It has to be that. And then stable under slicing and stable under change of base again. So those are the 2 important things. Okay, so we get finally to the theory of substitution, which allows you to consider fibers of families. When you have a term A, real A of A, and then you have a family P over A, then you'll get the substituted, you get the fiber P at A, which is a family in convex gamma. It will again be compatible with extension. The same story holds. There we will first introduce pre-substitution algebras and pre-substitution homomorphisms. And then the substitution algebras will be the ones for which substitution is a pre-substitution homomorphism. Okay? So just for that. So here's how you introduce substitution. Again, there will be 3 versions of this same rule. So if you have a term A of A and the family P, then you get P of A, which is in the context gamma. So you will lower the context by this. Okay, and the other 2 versions for the higher structure are these, and it's going to be compatible with extension. That's important. So it's going to be implemented as an extension homomorphism. That just means that the A distributes over the extension. So we have this extension homomorphism. This time the domain has to give a term. So we have to have a term A in T. Then we look at the boundary. The boundary is A, and we have some family of which the FT of which is underlying family is A itself. So it's a family above, it's the P. So it's going to give that structure, and the output is a new family over the context gamma, which is the same context, underlying context as the underlying context of A. So that means you have another commutative diagram. And then a pre-substitution algebra is one which has substitution. Why did I call it the pre-substitution? Well, it's the substitution homomorphism. Should I call it pre-substitution? Okay, so a pre-substitution homomorphism is one that preserves the substitution, so one that commutes. This is stable under slicing because you can define it in such a way. Well, by pullback, you can just do that. It's stable under change of base because you can define it using some complicated pullback diagram. And then, so because you have these two properties, it makes sense to require that substitution is a pre-substitution homomorphism, and to do that you get a substitution algebra. Okay, so substitution homomorphism is one that's between substitution algebras, and the whole thing is again stable under change of base and under slicing. Oops, no, these two things. That always holds all the time. And the fact that substitution is itself pre-substitution homomorphism, in the rules it shows like this: if you have a term A and a term G, and you substitute some family first by the G and then by the A, then you could have first substituted this thing by A, but now you cannot substitute by G anymore, but you can substitute by GA itself. And well, normally people would write this R A G of A. Normally people would write this as R A G of A, right? R with ordinary brackets even. That's just sort of what it is. Okay? And there are three versions of this rule, because there are three of everything. Yeah, doesn't make sense to say it long. Okay, so now we had this this picture where we were joining all the three theories, so I'm quickly going to say something about it, because it's nearly 3 o'clock.
Actually, you have, like, because we started late, so you have like 10 minutes.
Oh, okay, cool. So what do you need to do to join these three theories? We have these operations of substitution and weakening, and in the join of the theories, they have to be compatible with each other, right? Weakening has to be a substitution homomorphism, and substitution has to be a weakening homomorphism. And there are some more boundary conditions that I will say, but so here is the first: weakening is a substitution homomorphism. Substitution is a weakening homomorphism. There are rules for that too. Substitution has to preserve the units. So substitution is in fact a projection homomorphism. Weakenings are constant families. So if you look at A, B, and now you have a term A of A, so you're going to use it to substitute. There's only one thing that it can be, and this is B itself, and this is going to be one of the rules, and this is saying weakenings are constant families. And everything is invariant with respect to precomposition with units. How do you precompose with units? Well, if you have, I'll show that in the rules later on. That will be quicker. So a pre-E system is one where weakening is a substitution homomorphism and substitution is a projection homomorphism. A pre-E homomorphism is an extension homomorphism which is at the same time a projection homomorphism, and a substitution homomorphism. Okay, here's the rule that I just wrote down, that families are constant. Again, there are 3 versions of this rule, because there are 3 of everything. In a category with finite limits, you express this as a commutative diagram where you weaken, and around it you do nothing, but you make sure that you have the right coda line, and then you substitute, and that's the same thing as forgetting stuff. So this diagram says that that you have to do. So that's and then recomposition with the units. If you have a family P, now you can weaken this family P by A itself to pretend that it depends on A 2 times, and you can substitute the unit in this, and that's going to be P again. So that's another of those rules. There are again 3 of them, and some diagram commits. So you weaken on the top. Let's say you weaken, and then at the right you say, okay, you take the identity, the unit, that thing, that's the component, and you substitute, and it has to be an identity. Okay, so that's all there is. So any system is an extension algebra with a weakening operation on units, giving it the structure of a projection algebra. Substitution, such that it's a substitution algebra. I didn't talk about the empty context and the empty families, but they have to be there too. Such that, well, these conditions of weakening, substitution, homomorphism. Substitution is a projection homomorphism. Weakened families are constant. Recomposition with identity function leaves everything invariant, which was the last thing that I very quickly showed. And other rules well, about the empty context and empty families, but I didn't show them, so but there are these rules. So that's an E-system, is such an object in a category of finite limits. And then I'm going to end with this slide. So we just did the top thing until the dependent type theory, but you can of course go on and require that things are E-homomorphisms. So you can require that your pi is an E-homomorphism. You can require that you have a universe operator. You can introduce inductive types where the inductive principle is again an E-homomorphism. So you can do all these things probably. I didn't really do them, but I intend to look that up. That's possible. And then you join these theories, and I don't really know if you can get to independent mathematics, but requiring that all these things are compatible with each other gives you something. So I think maybe you get that independent mathematics. I'm not really sure. And then you continue because you have universes, you have lots of internal models, and using internal using the graph model in particular, or using maybe cubical sets, the cubical submodel to have higher inductive types as a geometric realization that can be open. And who knows where it extends further. So I'd like to end here.
If you take your E-systems
Yes.
on the one hand, and on the other hand you have BWS category families with sigma types, are they intertranslatable notions?
I am not very sure, but I think yes.
I doubt it. Why?
Because
everything you said I could translate as you were saying it into what it would be in a category of families with sigma type, so that's one way. What about the other way?
The sigma types are not going to give you the associativity that I had in these slides.
so in other
Oh, I see. Because they're only given up
Yeah,
to.
but
up
with,
to
so I don't, so using sigma types.
So you're more
it
strict in
won't
a way.
work. Yeah, so using
Yeah.
sigma types it won't work, but I think it can, there can be a strictification.
Yeah. Okay, so the
that makes
supplementary
sense.
question is then what's the advantage of an e-system over?
May I just add
Yeah,
something
sure.
to one thing which is very different here is there are no morphisms between contexts.
Right,
That's
but it's
fundamentally different because there you can have all kinds of weird morphisms between contexts which have nothing to do whatsoever with terms. Here there are none, and that's what makes the thing more canonical in a sense.
yes, okay. I mean that's true. I mean it's also morally, you know, I mean the notion of context morphism is derivable in type theory, so in a sense it's not the most essential thing in a category of families to have a notion of morphism between the contexts, but you're right. Certainly.
I mean, here one can define
Yes.
the
Yeah, you
category,
can define them using the
category
empty
structure
context.
from.
Using the empty context you also get the morphism between the contexts.
So that sounds like you can translate from an e-system into a category of families.
I'm not sure about that way. I thought you could go from the...
You wouldn't know what is a type because there is no way to say when a family has length 1.
Yes. So it's the other way that you probably can go from categories of families to e-systems, or that I would give more chance, because there you would just have a tower of types as a family. But the other way indeed, because you get extended, you have this extension operation on families.
But I mean, your extension operation on families is some sort of strict sigma.
Yes, but that makes it very different from sigma.
In what way?
It's strict.
All right, well, so they're rather very different.
So the things that you would like to, the way that I see it is that this extension operation is compares to sort of multiplication, and the things that you want to call types are the things that are neither the empty thing nor they are of the extended form, but they are sort of atomic things that are and then a sigma type has to be such an atomic thing and not of an extended form.
But
You can have infinite contexts here, by the way. There is nothing to prevent you to consider things like infinite contexts which arise from folds, for example, from infinite folds. Like you can, I guess, have something like that.
If you could in categories of families. So you couldn't do that.
just on the same line, isn't it semantically a bit problematic that you have the strict equality between sigma types? I mean,
No, I don't have strict equality between sigma types.
okay, but between these contexts and these extensions, I mean, usually it wouldn't be, they would be equivalent, right? That wouldn't be.
Yeah, but so it's important that they are not sigma types. They are really like towers of types on top of each other. Type and family and type another.
Yeah.
And
I
another.
mean, we call them telescopes, but for me,
Yeah.
I mean, the analogy for me is it's an iterated sigma type. I mean, how would you model this? I mean,
so you don't have to make the step to apply the operation sigma to anything.
no, I understand.
Yeah, but that's
I'm just saying you have like that usually associativity of products is not strict, right?
Yeah.
In this theory, it's strict.
Yes.
And I'm feeling, and then you even maybe put pi types on the top, and now the adjunction between pi types becomes strict as well. is this consistent? I mean, you've got a model in the sense where you can strictify all these equalities. I mean, all these equivalences.
These systems are model of this theory, I'm pretty sure.
Yeah, I'm reasonably sure. I mean, you can build this kind of things from usual types here.
Can you normalize all these isomorphisms to some canonical?
You don't make them isomorphisms. You just reason about contexts, which essentially talking about context together with some kind of points in them, which tell you that the context is kind of split into, let's say, into two. So the family would be just any context together with a natural number n, which is less than the length of the context, which kind of tells you where it's split.
Yeah, that's syntactical. I mean,
yes.
I'm thinking of, like, if I want to model this sort of semantically, if I want to model context as types, as sets, yeah, or types, and then context as extension as this pullback, then you make a sort of canonical choice here, which I find difficult to understand. I mean, I would think that these equalities should not be strict.
I'm not sure the point about the choice of pullbacks that you didn't understand. What was that? Can you repeat it?
I mean, if I model context extension by the semantic counterpart of what context expansion is, it's pullback, yeah. And then you have this equality means that you have a canonical choice of pullbacks satisfying some coherences, right?
Okay.
And I just wonder whether this is possible to do this.
I'm not sure. I think I needed the choice of pullbacks just in a category expansion. But I didn't need to have any coherence in there. So, but sure. I think I'm not answering.
Maybe my question is maybe. Sorry, I have actually another comment on this presentation.
Yeah.
There were some slides which were very easy to read, and some where in the end I gave up. And it turned out that the ones which were easy to read were the ones with types theory, and the ones where I gave up were the categorical ones. And I actually wonder, can you not write down all these conditions? I mean, for example, I just wrote down what an extension algebra is and so on, just using types theory and make it less obfuscated, or?
I did do that, right? I did two presentations, one with the inference rules, which is the one that you just asked for.
But not always. When you wrote about these extension algebras and these properties of these extension algebras, then you only do it diagrammatically, but you could have also used types theory, or maybe I'm wrong?
You can show you're wrong.
There are.
Yeah, sure. No, but later on you say, for example, an extension algebra is this. Yeah, here. Up. Why don't you say it in terms of types theory? I mean, this E0, I can write you down what E0, E1 is in terms of types theory, and then I can write down what this equivalence is, and it becomes much clearer.
But I did write it down. The upper thing here is the E0.
Yes, exactly.
And the lower thing is the E1.
Yeah.
So just didn't call them E0 and E1.
Exactly, but if you write down the next slide in terms of, I mean, E0 is an operator from context and family versus context to context and so on.
Yeah.
And then it just is normal. It's just normal associativity, right? Yeah. And I don't need this diagram on the next slide.
But you do need to know. So in this diagram, I'm saying that the underlying context of the extended thing is the gamma which we had earlier.
But this comes from the typing. I mean, this is part of the typing rule.
Yes.
Right? You don't have to write. But on the next page there's a diagram. There's this one.
Yeah.
And I mean, this just comes from very simple type theoretic reasoning, right?
Yes. So this is easy.
Which you did there. Yeah.
I did it. I did it here.
Yeah.
Exactly.
Yeah.
Yes.
Okay, and then you define what the associative one is.
Yes.
Which is also very easy if you write it down type theoretically, right?
I agree.
Yeah.
I mean, there are two ways to present it. I thought I gave the theoretic presentation and the categorical presentation. But I'm not sure what you want more.
No, but at some point you only do give the categorical rules and you didn't use type theory anymore, right?
So at some point I started saying first that things should be homomorphisms,
Exactly.
and then I gave you the rules.
This discussion offline.
Let me interrupt this. Because, I think we need to get